Pelton. This is Algebra 2, Chapter 6, Section 6, solving exponential and logarithmic equations. So we did all of the simplification and combination, condensing, expanding techniques using all the log rules in the prior sections, which all lead to this, which is solving equations. So these first ones will be exponential equations. The second half will be the logarithmic equations. Okay, so basically, an exponential equation is any equation that contains at least one exponential type term, which is a power with a variable in the exponent. So in this first problem here, you always want to follow the order of operations, but there's only one thing we can do here, which is get rid of the base here, which is a base 2 in the power. So how do you get rid of base 2? Use a log base 2. So log base 2, you have 2 to the 3x minus 8 equals log base 2 of 16. Because what you do to one side of the equation, you must do to the other in the process of solving, which is the properties of equality. So that cancels, gives me 3x minus 8. And 16 is 2 to the 4th power, which will also cancel, leaving me with 3x minus 8 equals 4. So I can do the add subtract step. So 3x equals 12, and divide by 3, x equals 4. And you can plug that in to verify that it actually works. So scenario 1 is where you have one base in the problem for an exponent type term, and you can just cancel it using in that base. Scenario 2 is where you have different bases, but each of these bases have a common factor of 3 in this case. So this is 3 to the 3rd, and this is 3 squared. So I can replace each of those terms with the new base. So using the power to power rule, I can simplify. So that's 3 to the 3x plus 9 and 3 to the 2x minus 2. Because power to the power rule is multiply. You should know your exponent power rules. Okay, so now I actually have the same base on both sides. So I can use the log equivalent, which is the inverse. So 3x plus 9 and log base 3 of 2x minus 2. So those logs, what you do one side of the equation, you do the other. A log of the same base cancels a power of the same base because they're inverses, leave me with 3x plus 9 equals 2x minus 2. So we'll minus 2x and we'll minus 9. So that leaves me with an x equals negative 11. And you can plug that in to verify that it actually works. Okay. All right. Next one, C, is very similar to B, except we need to do a slight modification with the bases this time. So 100 and 1/10 have a common base of 10 because this is 10 squared, and 1/10 is 10 to the negative 1. So now we can do our power rule and get 10 to the 2x and 10 to the negative 1x plus 3. So the key is when you have multiple bases, you always want to try to match them up if possible, which is not always possible. So I can do a common log to both sides. Well, why a common log? Because common log is log of base 10. So that leaves me with 2x equals negative x plus 3, right? Because they cancel. So if I add x, I get 3x is 3. Or divide by 3 and I get x equals 1. Okay. All right. She may also have multiple things to do in the problem, which you have to do order of operations, right? Which order of operations, good old grade school, is grouping symbols, um, exponents, radicals, and of course now we have logs in there. Multiply and divide and add and subtract. Of course, you go this way to simplify, right? Good old grade school, and then you go backwards to solve because you're working backwards to the solution. So add and subtract step is add 3. So 40 e to the 0.6x equals 240. That's the add subtract step. And then the multiply divide step is divide by 40. So we're moving backwards in the order of operations. So e to the 0.6x equals 6. Then we have the exponent radical log step, which comes next. So how do you cancel a base e? Well, you use a log of base e, which is otherwise known as the natural log. So those will cancel, leave me with 0.6x equals the natural log of 6. So the last thing is the grouping symbols, but we don't seem to have any, but we really do. These are in grouping symbols because the exponent of the power is an assumed grouping symbol. So the last step is to divide by the 0.6 or 6/10. So x equals the natural log of 6 divided by 6/10 is actually the answer. Okay, so that problem right there has a singular power of x, thus you must use the isolation technique to solve. When you have multiple powers of x, you have to use the factoring strategy to solve, and we'll do that down below here. So I'm going to shove it over to the right so I don't run out of room for e. So I'll do these out of order. So since it has multiple powers of x, I must do the factoring technique. So I'll just do it over here. Quad form factoring. So this is e to the x times e to the x will give me e to the 2x. And then 1 times 3 gives me 3, which is 1 times 3, or negative 1 times negative 3. Well, I think I want this one because that'll give me my middle term of negative 4 when I multiply it back. Okay, so e to the x minus 1 equals 0, and e to the x minus 3 equals 0. So e to the x equals 1, and e to the x equals 3 when I solve by adding those terms over. So I do natural log to both sides. That'll cancel there. X equals the natural log of 1. Well, the log of 1 for any log is 0. And then those cancel. X equals the natural log of 3. So we have 2 answers for this one. Okay, so the last scenario is the toughest one because neither of those bases match, and neither of them has a common base because 5 is prime, 2 4s are relatively prime to each other. So basically, pick a base, whichever one you want. I pick base 5. So log base 5 of 5 to the x minus 2 and log base 5 to the 4 to the 2x plus 3. Because what you do to one side of the equation, you must do to the other. You can't do one base to one side, one to the other. It's like adding 5 to one side of the equation, subtracting 6 from the other. It doesn't make sense. What you do to one side, you must do to the other. So those cancel. Leave you with x minus 2 equals. Now I'm going to take the power and bring it down using the power rule. So this is 2x plus 3 times log base 5 of 4. But this is wrong because it's the entire 2x plus 3 being multiplied by that log. So if I distribute that log, right, that log is being distributed into the parentheses now because I need to get x on one side of the equation. So that's 2x times log base 5 of 4 plus 3 times log base 5 of 4. So I need to add the 2 to the other side and subtract this log to that side. So I get, when I do the adding and subtracting, x minus 2x times log base 5 of 4 plus 3 equals 3 times log base 5 of 4 plus 2. So now I have all the x terms on one side, the non-x terms on the other. So I need to factor out the x because that's what I'm trying to get by itself. So that leaves me with 1 minus 2 times log base 5 of 4. I have an extra 3 in there by accident. I'm sorry. I'm going to get rid of that. That 3 should not be there. I don't know why I get that. Was the 3 of the multiple on the other side. Okay. And then this stays the same. Now I can divide by that long term. So those cancel. Leave my final answer of x equals 2 plus 3, or 3 plus 2, whichever one you want, times the log base 5 of 4. So a lot of you have tried to add the 2 and the 3 in the past, but you can't do that because order of operation dictates the multiply must come first, right? So you can't do that. That'd be not following the order of operations. Plus, they're not like terms. You couldn't add them anyways because it's not 3. It's 3 times a log. Make that better 5 than that. All right, so on bottom I have the 1 minus 2 log base 5 of 4. Oops, looks like I lost the 2 right there. Okay, and that is the... All right, so pause the video. Try page 2 for yourself. Okay. All right, page 2 is a base 5, so choose log base 5 to cancel. But what you do to one side of the equation, you must do to the other by properties of equality. So cancel, cancel, 3x minus 6 equals, and this is nice because 125 is 5 to the third, which cancels, so 3x minus 6 equals 3, or 3x equals 9, divide by 3, x equals 3, which works out splendidly. Plug that back in, it actually works, right? Because 3 times 3 is 9, minus 6 is 3, 5 to the third is 125. Okay, 8 and 4 are not the same base. However, 8 is 2 to the third, and 4 is 2 to the second. So if I replace those numbers with their new bases, we get this. Simplify, which is not solving. I get power to power rule, which is 3x plus 6, and 2x minus 6. Okay. I think we're good here. All right, so log base 2 on both sides. So those will cancel nicely because log bases cancel power bases. So we have 3x plus 6 equals 2x minus 6. So minus 2x and minus 6. So we get x equals negative 12. Okay. All right. So scenario 1 had one base. Scenario 2 had two bases, but we could match them up. Okay. So C is the same as is still scenario 2, which we don't have the same bases. We have multiple of them, but I can still match them up because 81 and 1/9 can match because 81 and 9 are both factors of 9 or 3. I'll do 9, so that's 9 squared is what my 81 becomes. And then the 1/9 becomes 9 to the negative 1. So that's 9 to the 2x equals 9 to the negative x minus 3 if I simplify. Okay, so I can use base 9 now for a log to cancel. Oh, I almost wrote plus. I'll erase that up. So we have 2x equals negative x minus 3. So we add x. So 3x equals negative 3, or x equals negative 1 is our final answer. Okay. All right, next one, we have multiple steps. You must follow the order of operations. So add 5 is a singular power of x. So this is, since it's a singular power of x, you have isolation technique. So that gives me 63. So the add subtract step comes first. Multiply, divide comes second. Exponent, radicals, and logs comes third. I have a power here, so I need to cancel the log. Which log cancels e? The natural log, which is log base e. What I do to one side, I must do to the other. So cancel, so I get 2x equals the natural log of 9. The last step is grouping symbols, which I do have because the exponent of a power is an assumed grouping symbol. So divide by 2. So x equals the natural log of 9 divided by 2 is our final answer. Okay, that is a singular power of x. If you look below that, the problem F has multiple powers of x, thus that must be a factoring strategy. That's true of all chapters, not necessarily this one. So if I do the factoring strategy, e to the x times e to the x will give me e to the 2x. That's 1 times 7 is 7. That's 1 times 7, or negative 1 times negative 7. Either one will give you. So I want the double negative in this case, because that'll give me the negative 8 in the middle when I add them, and the positive 7 when I multiply. So e to the x minus 1 equals 0, and e to the x minus 7 equals 0, using the zero product property of equality. So we'll add 1, e to the x equals 1, and e to the x equals 7. Natural log both sides. So that'll cancel, leave me with x equals the natural log of 1, or log of any 1 is 0, and x equals the natural log of 7. Okay. All right, last scenario, we have two different bases, 3 and 7. They're not the same, and they don't have a common base, because 7 is prime, 2, 3, so they're relatively prime to each other. So pick one. I'm going to pick base 3. So log base 3 of 3 to the 2x minus 1. You want to do to one side, I must do to the other. You can't do something different to the other side. Properties of equality. So those will cancel, leave me with 2x minus 1. I'll use the power property of logs to bring that down. So I have x plus 1 times the log base 3 of 7. So I'm going to distribute the log to both of the terms in the inside, because I need to get x by itself. So it's x times log base 3 of 7 plus 1 times log base 3 of 7. You really don't need the 1, but I'm going to put it there just for lesson's sakes. Okay, so we need to move the x term to one side and the non-x terms to the other. So I'm going to subtract that to the side. So if I do that, I get 2x minus x times log base 3 of 7 equals, the 1 went over, so that's log base 3 of 7 plus 1. You can't add the 1 to the 7, because order of operations in this case, the log would come first, plus 7 and 1 are not like terms, because it's not 7, it's log base. It's log of 7. Okay, so I can factor out an x, which is 2 minus log base 3 of 7 equals log base 3 of 7 plus 1. I can divide by that binomial term now. Whoops, I forgot the 2, didn't I? 2 minus log base, what do we have, 3 of 7. So those would cancel, leaving us a final answer of x equals 1 plus log base 3 of 7. And on the bottom, 2 minus log base 3 of 7. You can put the 1s and the 2s being adding, striking first or second. It really doesn't matter. I like to put them first myself. It's really a preference thing. All right, that is the end of part 1.